This is the fourth in a series of presentations on system requirements analysis based on papers I've given at the International Council on Systems Engineering. So this one was from the year 2000. The symposium was in Minneapolis, Minnesota. And in this paper, Fuzzy Sets as Requirements Antecedents, I was trying to examine the implications of some of the completeness criteria, the reality that you've got to attempt to cover the complete physical space of inputs. So I wanted to look at whether using fuzzy sets would help in that methodology or in achieving that goal. So my objectives here for the attendee to understand why we might consider using fuzzy logic, and I'll explain a bit about fuzzy logic in a few minutes, as a means to handle tolerances and ambiguity, because inputs get processed differently in different domains. So there's always some uncertainty about what was actually received. So we'll talk about fuzzy processing methods and then some of the implications for how these can be used in writing requirements and implementing requirements. So fuzzy sets use a natural language or rule-based approach to processing. And I thought, well, natural language is what we do in requirements, so perhaps fuzzy sets might be useful in helping us do a better job on that. So we have an if-then condition or stimulus response or an input-output, but something comes in and it is interpreted, and then some decision is made, and the system is supposed to yield an output based on what the inputs are. The benefit of fuzzy sets is they inherently address ambiguities and imprecision regarding these input parameters. In other words, it's not an either-or kind of thing. It's, well, this is mostly like this, and this is what we mean by fuzzy sets. It's mostly like this, but it's got some of that. So can we use that idea to help us do a better job in our requirements analysis? And so we expected a positive synergism in using these fuzzy sets to help us describe the input conditions, that is, the antecedents in the requirements. So an example, and I used TTL logic in one of my first technical jobs back in the 70s, transistor logic in discrete electronics. So inputs are either 0 or 1, so this is binary, and this is great for software kind of processing. It's either this or that, and the definition in the TTL standard is anything below 0.7 of a volt is called a logic state 0, and anything 2 to 5 volts is a logic state 1, and anything between those two is undefined. So that means if for some reason a system were to receive an input in the range of 0.7 to 2 volts, it would be unclear or indeterminate what the actual output of the system would be. And remember from our prior SRA discussions, one of the things about completeness is we have determinate behavior for all possible input conditions. So how to handle this indeterminate state, and can fuzzy sets help bridge that gap? So tolerancing as a standard means to handle this sort of a thing. So in this case, we might even look at not just what the ranges are, but if things are changing, where are they and what direction are they moving? So hysteresis comes to play. So in this example, we can define a tolerance band around some nominal range and describe in detail what the behaviors are. So in some intermediate range here, then we have some specific behavior we require. And the question is, what happens as we move across these boundaries? So we might write requirements that explicitly include not only where we are, as in each of these thresholds, A, B, C, and D, and also what direction something is changing. So if we're at A and we are decreasing the value of that input parameter, that independent parameter P1, then we have to change state. And we can write the requirement that way. If we're at A, but it's increasing, then we wouldn't force a change. That would mean that either the current state is acceptable or a different state is acceptable. Similarly, at B, if the parameter is increasing, then we have to change the state. But if it's decreasing, then we might change the state. So multiple outputs might be possible. And this apparent lack of determinacy is perhaps a problem. We don't exactly know what the system is going to do for any given input condition. And that's not a very satisfactory position to be in. So I wondered if there's a different way of defining these inputs and changes so that we always get determinacy. In other words, no matter what the input is, how it's behaving, we always know exactly what the output is going to be. So I decided to, well, let's apply fuzzy set theory. And the first thing we do is construct a membership function for the transistor logic. So in fuzzy logic, you describe the degree of membership. That's a probability, if you will, from 0 to 1 that says over a certain range, in this case, from 0 to 7/10, the membership function in the state 0, the binary state 0 is 100%, and the membership function in the binary state 1 is 0. And similarly, for the value of 1, above 2 volts, the membership function for 1 is 100%, and the membership function for 0 is 0. So that preserves the standard definition of TTL. It's this intermediate area between 0.7 and 2 volts that becomes interesting. And here we've just used a linear membership function that says in between 0.7 and 2, the membership function is the weighted average of the two inputs. So we have linearly decreasing from 1.0 to 0 for the 0 state, and linear increasing from 0 to 1 for the 1 state. So these are membership functions, or if you will, probabilities that you would be in one state or another. But we have to define the membership function for all output states based totally across the whole parameter range. And I haven't gone below 0 or above 5 in this example. So what does that mean? Well, if our rule is that we want to select the output state based on the highest degree of membership, there's a crossover point at 1.35 volts. because anything below that, the state 0 dominates, and above that, the state 1 dominates. So I've eliminated this no person's land in between, and now I have determinate behavior above and below 1.35 volts. And now we might get into an argument about, well, how close to 1.35 volts, because now I have a sharp boundary issue. So, but there's no ambiguity. It's either going to be an output of 1 or an output of 0. But we may run into trouble because now we have an explicit sharp boundary at 1.35 volts. Otherwise, the system is defined completely in terms of its output behavior as either 0 or 1, regardless of where the input resides, anywhere from 0 to 5. And we could extend these to minus or greater than plus 5 if we wanted to. In general, the way we do fuzzy processing is we apply all the rules concurrently to determine where the maximum value is. So their degree of truth, if you will, how well the rule antecedent is satisfied by the current state. So we can associate several rules with all possible values of the input parameters. And that's different from normal requirements, because in normal requirements, we have a set of inputs defined with respect to an output, and we only process that condition, that requirement, when those inputs are true. In fuzzy processing, you process all the outputs and then determine, generally for all the rules, where's the output, where's the maximized output. It's a sum over all the rules of what the output is times its truth value, or its degree of satisfaction based on the input state. So if we are at level 0 or at 0 volts input, then the truth value for the output state 1 is 0. So we get 0 output. On the other hand, the truth value for the output state 0 is 100%. So it's easy at 0, and this covers this intermediate range according to the linear change of the voltage and the membership functions that I talked about on the prior slide. So what we determined that we have to do a few things in order to use fuzzy sets. We have to define the membership functions as part of the requirements. So it's not just 0 and 1, or 0 or 1 as an input. We have to say what the degree of membership is based on where you are in that total parameter space of 0 to 5. The second thing we have to define is how then to process the inputs according to, for example, the algorithm on the prior slide. What's the if-then syllogism? And that includes the specification of this fuzzy logic processing. How am I going to actually calculate the output based on where the inputs are? And as soon as you get into the word how, now we're really getting into design. So it's no longer so much a requirements orientation, but now we're going to specify how the inputs are to be processed and the algorithm by which they're going to be processed. And the other thing that we realized was that if you had a different fuzzy processing rule, you might get different results against otherwise identical requirements. So it seemed to me, as a result of doing this, that the machinery of fuzzy logic is not well suited for requirements, because we still end up with this sharp boundary tolerance issue depending on how you construct your membership rules and processing logic. And we have to put in much more machinery in the requirements that relate to fuzzy logic processing, the membership functions, the processing syllogism, how we're going to determine which is the appropriate output. So it seemed to me that this probably isn't the best way to go. And we may just have to live with the idea that there may be some areas of input conditions where we simply don't prescribe the output. And in the requirements, we could say any output is okay in this range, or simply stay in the situation you're in, the current state, until you actually cross a threshold. So for example, in transistor logic, you stay at 0 until you hit 2, or you stay at 1 until you hit 0.7. So it's a hysteresis kind of description. And then that covers that no persons land between 0.7 and 2 because you don't do anything, you don't make a state change until and unless there's an actual transition across the boundary. So in summary, while fuzzy machinery can provide an alternate mechanism to treat tolerances and imprecision, and it does provide a rule-based formalism, it's probably better suited for design implementation rather than requirements. And once I completed this analysis, I've actually never used fuzzy sets to attempt to define requirements, natural language or otherwise, because I concluded that this machinery is really not suitable for requirements. And that will be my discussion for today, and I thank you very much.